Welcome, Calculus. This is Section 8.8, Improper Integrals. The central question is, what makes an integral improper? Let's begin. So the definition of a definite integral, we've done this before, the integral from a to b of f of x dx. So a and b have to be real numbers, so maybe like 1 to 2, and so it's a finite interval. Furthermore, your function f of x has to be continuous on the interval. Well, what we're studying here is cases where that's not the case. So sometimes this is going to be where our integrals, instead of going from finite numbers, we might go to infinity or go to negative infinity. Or sometimes where the function's not continuous, like it's got an asymptote in the middle. What do we do in those cases? So these kind of integrals are called improper integrals. So let's take this case. So integrals, a function has infinite discontinuity when the limit of that function at some point c goes to infinity or negative infinity. And this happens when you have an asymptote. I think this is just tote. I spelled that wrong. So let's say if we said we had an asymptote, let's do the function y equals 1 over x. That function's an inverse function. It looks like this and like this. So you got an asymptote here on the y-axis, an asymptote here on the x-axis. So if I said the limit, in this case as x approaches 0, well, 0 from the left-hand side is going to actually equal, this function f of x is going to actually equal positive infinity. But if you did the limit as x approaches 0 from the right-hand side of f of x, that is approaching negative infinity because it's going down forever. So that's what you mean about infinite or discontinuity. Now, definition of improper integration. So really what's going on here is I set up an integral like I'm going to go from some number a, and make this a little bigger, to my upper limit's going to be like infinity. So I'm going to keep going on forever. So the way we can actually think about this is the integral of from a to infinity of f of x is actually the limit as some number b approaches infinity of the integral of f of x from a to b. So really we're taking this infinity and we're just substituting this variable b for it, and we're saying the limit as b approaches that infinity. Infinity is one of those weird cases. And kind of a sidebar here, we sometimes say like 1 over infinity equals 0, and that's kind of a simplified form of saying like, well, the limit as x approaches infinity of 1 over x is actually equal to 0. So infinity is one of those weird cases where we're actually talking about limits when we're talking about evaluating it. And some other notes here, like e to an infinity power is going to be infinity, and let's see, infinity times 5 or some number is going to be infinity, but infinity times like a negative 5 negative number goes to negative infinity. You're also going to say square root of infinity is going to be infinity, and the natural log of an infinity is going to be infinity. So those are important things to know as we do this. Same thing here. If I can go from negative infinity, so instead negative infinity to a finite value b, I can plug in an a for that negative infinity and say a limit as a goes to negative infinity. Now, the third case is interesting. If f is continuous, what if we're going from negative infinity to positive infinity? They both go on forever. Well, I want to break that up, and I pick some value in between. So we're going to call this some value c. And I can break that up in the integral from negative infinity to c of f of x plus from c to infinity of f of x. So sometimes we might pick a value that's actually like an asymptote or something in the middle of the function, and then we can follow the rules above in 2 and 3. Some notes on vocab. We say a function converges if the limit exists. It's an actual real number. It diverges if there's no limit. So that happens when we have like infinity or negative infinity. And that's going to be important as we go into chapter 3. So let's evaluate this example. So the integral from 1 to infinity of dx over x, which is the same thing as saying the integral from 1 to infinity of 1 over x dx. So I can rewrite that one like the following. I can rewrite it as a limit function. So I'm going to say my limit as, since it's the top, b approaches infinity of 1 to b of 1 over x dx. And so integral of 1 over x is going to be the natural log of x from 1 to b, which is the natural log of b minus natural log of 1. And natural log of 1 is 0, so I can say that's just the natural log of b. But it's natural log of b, oops, pen's messing up. It's a natural log of b as the limit as b approaches infinity. So that just becomes the natural log of infinity, which is just infinity. So we can say this diverges if we were asked that question. Now, here's another way of doing this. You understand that limit stuff? If I were to evaluate these kind of problems, and if this is an AP test, these could generally show up as multiple choice questions. Just evaluate it as the infinity. Like, don't bother setting it up as a limit. So I would just say, okay, well, the integral from 1 to infinity of 1 over x dx, well, that's just ln of x from 1 to infinity, which is just ln of infinity minus ln of 1, which is ln of infinity, which is just infinity. As long as you're comfortable with the infinities to solve these kind of problems, that's all you have to do. Generally, these show up in multiple choice on an AP test. So here's a graph of that example. We're actually 1 over x, and this is the right-hand side. It's going from 1 all the way to infinity. So even though it's getting smaller here, this section will continue to grow forever. So we say this diverges because it has infinite area. Infinite discontinuity. So sometimes the function's not continuous. So that's like going back to that. If I did an example here, I'm going to say, I don't want it to be straight up and down. So what if we go back to the function that's 1 over x again? So y equals 1 over x. And then, again, you have that asymptote. So I'm going to just worry about the right-hand side. What if I said, what's the integral from, in this case, like 0 to 1? So 1 is right here, so I'm just asking for this area like in here. Well, you can't just say 0 to 1 of 1 over x dx. The problem is this approaches 0. We never actually hit that 0. So if I'm following my rules that I used to know for these infinities, it's going to be the natural log of x from 0 to 1, which is natural log of 1 minus natural log of 0. I can't do log of 0, so what's going on here? Well, you have to understand that we treat this as left or right-hand side limits. So I'm going to rewrite a problem like this. And this is going to be similar to example number 2 in this case, where I'm rewriting this lower limit a. I'm saying, well, the limit as our variable c approaches that a from the right. So I'm going to rewrite this one as I'm going to put the value c to 1 of 1 over x dx, but it's the limit as c approaches 0 from the right. So as you're approaching 0 from the right when you evaluate this, again, it's going to be the ln of x from c to 1. So ln of 1 minus ln of c, so which is just going to be negative ln of c, and limit as c approaches 0 from the right. So as it's getting closer and closer to ln, well, what happens is when you get closer and closer on the natural log function to 0, you're actually going down. You're going to negative. So this is going to be negative infinity, because the minus from the ln of x, which is just positive infinity. So this actually diverges again, and we have a discontinuity of infinity. Oh, I don't have a picture of this. I wish I did. Oh well. Let's try another example. So I want to evaluate this function, and I actually drew the picture right here. So those ones all diverge. Let's find a case where it actually converges. So it's the integral of 1 over the cubed root of x from 0 to 1. And you can't do 0 here. We have this asymptote because if you plugged in 0 for x, you'd be dividing by 0. So in this case, let's just evaluate this. Let's set up our limits. So it's going to be the limit as, I'm going to say, c approaches 0 from the right, the integral from c to 1 of 1 over cubed root of x dx. I can rewrite that as the integral of x to the negative 1/3 power dx. Integrating that with power rule, that becomes x to the positive 2/3 times 3/2 from c to 1, which is going to be 3 times 1 to the 2/3 over 2 minus 3 times c to the 2/3 over 2. All right, and remember, it's the limit as c approaches 0 from the right. So if I just plugged in 0 at this case, so 3 times 1 cubed is going to be 1 over 2, so 3/2, minus, you plug in 0 for this, well now it's 0 to the 2/3 power, and that's just 0. So it's 3 times 0 over 2, which is 0, so my answer is 3/2. This actually converges here. It converges at 3/2. So the area, even though we're approaching this, it's going to converge to 3/2. All right, let's do some examples. Pause the video. Okay, I'm going to evaluate these integrals. So I'm just going to leave the infinity in. So integral of e to the negative x is negative e to the negative x from 0 to infinity, which is negative e to the negative infinity minus negative e to the negative 0. Well, negative infinity is same thing as negative 1 over e to the positive infinity plus e to the 0 power, so which is plus 1. 1 over e to the positive infinity is 1 over e to the infinity, which is 0 plus 1, which ends up being 1. The bottom one in this case, integral of 1 over x squared plus 1, that is actually going to be arctangent of x from 0 to infinity. This gets tricky. So which is going to be arctangent of infinity minus arctangent of 0. Okay, arctangent's weird. Tangent's weird because you don't have those memorized. And arctangent is the inverse. So when does infinity happen? Infinity happens, and we're thinking unit circle, when you have 1 divided by infinity. So this is where your sine is, and if we're talking tangents here, it's where your sine is 1 and your cosine is 0. So where does that happen on a unit circle? That happens, and we're talking tangent domain, which is going to be on the right side. That happens right here on the top. So it's going to be pi over 2. Now, arctangent of 0, where does that happen? Well, that's 0 over 1, so your sine is 0 and your cosine is 1. That happens when your y is 0. That's going to be right there, so minus 0. My answer is pi over 2. Wait, let's evaluate this. We will save this for class. We're done.